Hello everyone, welcome to our channel Code with Sunny, and today in this video we are going to discuss a hard problem, largest rectangle in histogram. You can see over here its index is 84 and it is a hard problem as I've already said. Okay, so the thing that we are going to learn in this video is like two of the things. Like we are going to learn how we can use a stack. Like you must have heard the stack data structure, and we are going to use the stack to find out next greater element for every index in an array, and also how we are going to use the stack with the concept of next greater or next smaller element to solve this problem efficiently, like finding out the largest rectangle in the histogram that is being given to us. Okay, so yeah, so let's begin. So given an array of integers, heights, and representing the histogram's bar height, that is, if you have been given the height as 2 1, you can see the first height of the histogram is going to be 2, and the second one is going to be 1, and third one is 5 6 2 3, like that. Okay, where the width of each bar is 1. You can see the width of each bar is 1, and return the area of the largest rectangle in the histogram. That is, there must be a rectangle that we can form in this histogram, and we need to maximize that area. Okay, so I am going to discuss in this video the O of n time solution and O of n space solution efficiently, how we are going to do that. For that, you can easily see that we need to do some pre-calculation. I will explain it out what I am been talking about for the from the very beginning. Okay, so first look at the constraints, how this is going to help us. So if you have been watching my videos constantly, you must have been noticed that every time I have been talking about the constraints first, because it will give us the idea how and what type of solution we want, like this problem is going to demand, and what is the best way to solve this problem with the under the given constraints. Okay, so n, like the total number of bars is max, or like 10 raised to the power 5, that is the maximum number of bars, and heights of I is 10 raised to the power 4. Okay, so you can see over here, so the maximum number of histogram bars is 10 raised to the power 5. So we must frame a O of n log n solution or O of n solution in the best case. So O of n square solution is not going to pass because the number of iterations will be greater than 10 raised to the power 8. So in that case you will get a TLE vertex. So we would be looking for O of n time and O of n log n solution. So in this video we will be talking about O of n time solution. Okay, so let's understand this problem with the help of examples. So you can see over here I have already drawn the histogram. Okay, so this is actually a bars, you can see. So let me write down the heights of the bars. I picked from this example, you can see 2 1 5 6 2 3. So its height is 2, its height is 1, and its height is 5 6, then 2, and then 3. Okay, now you need to maximize the area of rectangle that is being formed over here. So the very first concept is, let me write down first concept. Okay, so let us draw any rectangle. Okay, so you can see that this is a rectangle and it has some length and it has some width. Okay, now if you try to explore all the possibilities of rectangle in this histogram, then it will be a hectic task. So in that case, what we are going to do is we are going to fix the width of a rectangle, that is this one. So if we are able to fix this width of the rectangle, that is W is fixed, then we can find out, like we need to maximize this L, maximize. Okay, so if you're not getting it, let me write down over here again, fix the width of rectangle. If you are able to do that, fixing the width of the rectangle, then maximize the length of the rectangle, maximize the L. Okay, now there are many possibilities of having the width of the rectangle. Likewise, let us say that if the width is this one, like I'm talking about this one, this is actually the width. So here you can see width is coming out as 2, right? So if width is 2, we need to maximize the L. Okay, So you can see, if I will consider this as the width of this rectangle, okay, that is this height. Okay, so let me just that is the height will always remain as 2, that is the width, and we need to explore the L to the right side and to the left side. Okay, just tell me one thing, that current length is at this position and at this position, right? So it would be better if I am going to write down over here, if my left bound of this length is over here and right bound of this length is over here. So we need to maximize the L, right? So this is L left and this is L right. So what we are going to do is we need to shift this L right to as far as to the right of this current position, and shift this L left as far as to the left of this current position. Now just tell me that if width I have already fixed 2, so if I will extend this L right to the next step, that is over this position, is it possible to do that? So let's draw the diagram. So you can see my L left is still over here and L right is now, it becomes over here. Now you can see this part is not lying in any of the histogram bars, so this is wrong. So we cannot extend this L right to the next position. And similarly, so width is 2. If you are fixing this L left over here, we need to extend this L left as far as to the left of it. So you can see there are no more parts over here, so we cannot extend L left as well as L right. So it means that left position of this length would be over here and right position of this length would be over here. And width we have already fixed. Width we have already fixed. So what is the maximum area by fixing this width? You can see width is 2 and the length that we are going to get is 1. So maximum area comes out as 2 when we are fixing this width. Now there are total n possible widths in this array, because we have been given n inputs of histogram heights. We are going to fix each histogram height, which will be our width, and try to find out the maximum length. Okay, yes, so what we are going to do is we are going to take out the another example and try to understand how we can do that. Okay, so let's say we are going to fix this one. Okay, yeah, that is width as 1. So let me write down width as 1. And if I am doing that, my left bound of this length would be over here and right bound of this length would be over here. Now, okay, now width is already fixed. It means that we need to, the rectangle can be like currently my rectangle is only over here. You can see. Now you need to extend this right as far as to the right of it and extend this left as far as to the left of it, such that we are going to have a rectangle covering some histograms. Okay, so you can see, let me extend this right to next step, that is this one over here. So you can see still I have the valid rectangle because it is covering the histogram. But if you notice over here, that is extending this right to the next position is not a good choice. Why? We can extend right to further more positions to the right of it. That is, we can extend right to up to this position, you can see. Okay, now can we extend this left? Yes, we can extend this left up to this position. Note that the height of this rectangle, that is the width over here, is going to be fixed. So my rectangle would come out to be over here. So this is my rectangle. If you can't see that, let me just highlight it. So this is my rectangle. I know my drawing is not good, but still I would help you to learn the concept efficiently. So this is my rectangle, right? Because we can extend this right. So right would become over here and extend this left to this position. Okay. So it means that fix the height of each histogram as your width and try to maximize this L. That is moving the right bound of this length as far as to the right of the current position and moving the left bound to as far as to the left of the current position. Now the thing is how you are going to do that. If you are fixing the width of each histogram, then it would take a time of O of n, and finding out the maximum L to the right of it and to the left of it would also take of n in worst case, so complexity would be O of n square. As I've already said, O of n square will not going to pass. So how we are going to find out this maximum L and to the right of it and minimum L to the left of it efficiently. Now this is going to be important. So the concept is next greater element, next smaller element, I think, but yeah, next smaller element we are going to use. Now just tell me, if I have already fixed this width, what is the next smaller element of the value 1 to the right of it? You can see all the values are strictly greater. Okay, that's why we are able to extend this one to the rightmost position. Okay, that is the key concept. Okay, just tell me one thing that again, so the value over here is, wait a minute. Okay, so what is the next smaller element of this value 1 to the left of it? You can see all the elements are greater. That's why we are going to able to extend this left bound to this position. That's why my rectangle is like this one. Okay, just take another example. Let's say I have fixed this one, that is width is 5, that is the height of the histogram is 5. Now just tell me, what is the next smaller element of the value 5? So the next smaller element of the value 5 is coming out as 2. That is the first smaller element to the right of the current element 5. That is being the first smaller we are going to encounter. Okay, so 5, that is this position. Now what is the next smaller element, that is the first smaller we are going to face to the left of it? You can see it is the value 1. So okay, so it means that if we are fixing this as the width of this rectangle, you can extend only up to this position. Okay, only up to this position, because if you extend like over this one, you can see the value is lesser than the value 5, so you cannot extend. So this will be our L. Let me write down L right. And what about the L left? You can see the next smaller element to the left of it is 1. So if you extend it like over here, this is not possible, so you have to stop it over here. So it would be like this one. So this will be our L left. So this will be our length, which will be coming out as 2, and this is our height, which is 5. So it means that we need to have the if we are able to find out the next smaller element for every index, then we are done. We can easily find out the maximum area by fixing each height of the histogram. Okay, so how we are going to find out? So we are going to use a stack. So let me just erase it and write down the concept of a stack. Okay, stack, which is helps in find next smaller element. Now, so the very first thing I need to tell you about stack is going to always store increasing elements. Okay, that is stack. Stack will always have the elements of this type, like 2, 3, 3, 4, 5, 6, 7, and let's say 7, 8. It will always have elements having the value of this type. It cannot have the elements of like 4, 5, then you are going to face 4. We are not going to have the elements in the stack of this type, because we need to find the next smaller element. I will tell out the concept though. So first you need to understand the stack will always contain this type of element. So if we suppose we have find out the value 4, we will pop out the value 5. So the stack will always contain an increasing order of elements, so it will be like this one. Okay, so what is the concept that I am going to use is, let me do some iterations and explain you how the stack is going to work to find out the next smaller element. So first of all, I will insert this value 2 in the stack, 2. Okay, now in the next case I will insert the value 1. Okay, now just think about that. 2 is greater than, sorry, 1 is being smaller than 2. As I have already said, we need to store the elements in the stack in increasing order, like in non-decreasing fashion. Okay, so it means that 1 is smaller than 2. So what we are going to do is we are going to pop out this 2. So my stack would become the only 1. Now because since the stack becomes empty, we are going to push back this element 1. So if you have noticed this one thing, that we have already find out the next smaller element of 2, because you can see this is the first smaller element to the right of this 2 which we are facing right now, because all the elements so far I have been visited is in increasing order. And if we have faced some smaller element, you can see the first smaller element would be 1 for the element 2. So we are going to mark as the smaller element of this 2 is 1. Okay, note that we would be actually storing the indexes, like indices of each positions. Okay, now the next thing we are going to do, so this is the current state of stack. Okay, now the next thing is like we need to store the value 5. You can see stack is 1, now 5 is stored. You can see still every element is in increasing fashion. Now next is 6, right? Now when you insert this 2, you can see 2, now the elements doesn't satisfy the criteria of increasing order. It means that next smaller element of 6 is 2. You can see 6 is 2. So in that case you will mark down the next smaller element of 6 is 2 to the right of it, right? And again, if this is good, we will pop out this 6. Now compare this 5 and 2. You can see next smaller element of 5 is 2. As I've already said, you can see the next smaller element of 5 is 2. Okay, so you are again popping out this out, so stack will contain 1 and 2 finally. Okay, so 5 has the next smaller element as 2. Now you can see still I haven't filled out this position because all the elements are still in increasing order. You can see. Okay, now comes the element 3. If you write down over 3 over, still it is satisfied. Okay, you can see 1, 2 and 3 are still in increasing order, so their next smaller element doesn't exist in this array. So for by default I will say that next smaller element for these positions are some, let's say, int max. We are not interested in that. Okay, so similarly, if you are able to find out next smaller element of each position of each index to the right of it, we can also find out in the reverse way also, like what is the next smaller element of this 3 to the left of it. You can see it is 2. And similarly, what is the next smaller element of this 2 to the left of it, which is, you can see, 1. What is the next smaller element of this 6 to the left of it, which is 5. You can use the same concept of stack by iterating in a reverse manner. I will explain it out in the coding part also. So this is 5, next smaller element to the left of it is 1. So you will write down 1 over here. And for 1, next smaller element to the left of it doesn't exist. And for 2, it doesn't exist. Okay, so similar is the case of the you are going to find it out. Okay, so yeah, we have already find out the next smaller element of for each indexes, so we can easily find out the answers. So let's look out the code in the how we can do that efficiently. Yeah, so you can see I have written a well commented code that will help you in understand the concept efficiently. So you can see time complexity is O of n because every element is going to be visited n times. N times. So it will, like, if you use a stack, every element is going to be visited exactly one time, and space complexity would be O of n because you would be using a left array and right of array to store the next smaller element position for every index. Now, okay, so stack of indices, stack that is going to help in finding the next smaller element. So note that we are storing the indices. Like in this concept, I have said that what is the next smaller element of 1? You can see it is 2. Sorry, 1 doesn't have any next smaller element to the right of it. Okay, so let's talk about 5. So next smaller element of 5 is 2. So we are storing the value 2 as over here, but in our code we need the position of this 2. Okay, so we would be storing the positions. So stack will help in finding out those positions. So I will iterate in this array, and while index is not empty, suppose we have non-empty stack, and we will compare that heights of I, that is the current value. Let's say we have the elements in this fashion. So you can see 1, 5 and 6 has already been occurred. Suppose we have now encountering the 2. So I will compare heights of I, you can see, with the stack stop, because these are the elements occurring in this stack. You can see heights of I is less than the heights of index dot top, that is stack stop. I will assign the right of this index dot top, that is the 6. 6 has the next smaller element occurring at the index I, and I will pop it out because we are done with this one. Now again, index dot push when all the elements have been satisfying the increasing order criteria. You can see 6 will pop out, 5 will pop out, so finally we will have 1 and 2, and you can see I am pushing out the 2 finally over here. Okay, now clear the stack if it contains some elements. because it might be possible that you can see if you find out the increasing order, like next smaller element to the right of it, you will have the stack in the final state as this one, 1 2 3. It will contain some element, because I am using the same stack to find out the next smaller element of every index to the left of it. So the concept is similar. You will iterate from the back side, you can see. So while index is non-empty, and you will do the same condition and assign its left index for every element. Now the concept is we need to find out the maximum area of rectangle by fixing the width and finding the maximum length. Okay, so you need to correct it over here. This will be length. Fixing the width and finding the maximum length. Okay. So W is heights of 5, which we have already fixed, and the max length would be extending the L left and L right as far as to their corners. So right of I and left of I will give us the value, and we need to subtract 1 to adjust the correct length. So max area would be maximizing the value of max area with L into W. That will be the length, and this will be the weight, and finally return the max area. So this will give you all test cases passed. Okay, so I've also submitted one another code. You can see this is quite optimized version, but it is quite difficult to understand. So still I will be sharing this code, and I will recommend you to try to understand this code, because it is like you need not to have extra two arrays to find out the left smaller elements for every index and right smaller element for every index. Okay, in that like in this code you need to do the every operations directly. So I will be sharing this code, and I hope you guys still still got this one. Then that's good, and if you are not able to grasp this code, then I would recommend you to comment over there, and I will help you guys to understand this one. Okay, so thank you guys for watching this video, and liking stay connected, and do like my videos, share my videos as possible, and thank you.